Hello, and welcome to Physics for Play. In this episode, we will continue exploring the damped and driven simple harmonic oscillator. We'll complete the solution by showing you the complementary solution in addition to the particular solution, which we've already covered. And we'll explore some of the physics of transient states that are associated with the simple harmonic oscillator. And we'll be doing this using the differential equation solver, DSolve in Mathematica. Let's get started. So to recap, we have been looking at solutions for forced harmonic motion and resonance. And we've gone through how to solve the differential equation when you've got a forcing function, f naught cosine omega t, which can also be written as the real part of a complex exponential. We have gone through the simple undamped case. We've gone through the case where there is damping. And today we're going to be using Mathematica's DSolve function to automatically come up with the solutions that we don't have to go through, make a guess, and then check the solution and verify that it actually works. We'll also explore a little bit of the physics of transients, which have to do with the second solution, which we're going to talk about today, which is the complementary solution. So if you will recall, we had a differential equation that looked like this. And I've actually switched this up just a little bit. So we originally had mass times acceleration equals minus kx minus b times the velocity plus f naught cosine omega t. I've moved the Hooke's law spring force and the damping force over to the other side because I think it'll help with what we're going to show here. Because everything on this side appeared in the original damped oscillator without any sort of forcing function. And we could have written that equation for the damped undriven case like this. Just basically set this term equal to 0. Everything else matches up 1 to 1. Now, here's where having this be a linear equation plays an important role, because with a linear equation, you can combine different solutions in superposition. And if I look at the damped undriven case at the bottom here, I can see that if there's a solution for this equation, well, I could add that to the solution for this equation, because the solution for this equation, if I plug in an x of t that gives us this, it's just going to be adding 0 to the equation. And that, of course, is also going to represent a solution since it won't change anything else on this side. Copying from the solution from the damped undriven oscillator case, we saw that the solution was this. So I have to be able to add this this solution into the original solution that I found. So you may recall that we found a solution for the particular solution for the differential equation when we had the f naught cos omega t in it. This solution for the damped undriven case is known as the complementary solution. So I've got to have a term like this in addition to the particular solution. And the way to understand these two different solutions is if you wait a long time for the system to come into some sort of steady state, then the solution that gets described is the particular solution. But initially, if you have some initial velocity or displacement, your motion is going to be very early on described by this equation, but this equation is going to damp away very quickly. So you've got this exponential decay. The exponential decay will make sure that this solution goes to 0 over some time scale. So this motion won't matter. in the long run, but in the short run, it'll affect what the motion looks like, what that motion looks like. This solution, including the complementary solution, can give rise to what is known as transients, or the transient motion of the oscillator. So we're going to look at those transients today and explore the physics of that. And just like we've done with all the other examples, we're going to show how to do this using the Mathematica's differential equation solver, DSolve. So in general, we know, as we've done with all the other cases, that we can solve, if it's a linear equation that has a solution, we can write down the differential equation we want to solve, plug that into DSolve, tell it the function we want to solve for, tell it the dependent variable of that function, and that will get us, that will tell us, we will get, oops, I need to, once again, need to quit my kernel because I've defined some variables here last time I tried to plot things out. But I can run this and I can get the general form for the solution. I can simplify that a little bit by making some algebraic substitutions. So as we've done in previous videos, we are going to write the stiffness of the spring constant K, in terms of the natural frequency omega naught. We are going to rescale the damping constant by a factor of m, m being the mass. And I'm going to write my solution as the solution to this differential, the solved differential equation. Now, what you will notice is that we've got two different solutions here. And we do have some constants. We've got a C1 here and a C2 here that will be set by the motion of by the initial conditions, so the initial position and the initial velocity. I also have a term here taking into account the forcing function, which has the F naught in it. So this part right here, the second part, is the particular solution. You've also got this complementary solution in the first half. So DSolve will get you both the complementary solution and the particular solution without any extra effort on your part. So again, Mathematica is your friend, and it does that for you. So we're going to go ahead and explore the solution here. I am going to go, let's define some constants. So we'll say K is 1. We'll give it a mass of 1. We'll give it just a little bit of damping. We'll make the amplitude of the driving force 1. And we'll make the driving frequency is what we'll change. So we can change the driving frequency to be close or far away from resonance, depending on what exactly we want to do. So I am going to copy and paste my differential equation solver down here. I'm going to actually make a list here and plug in some initial conditions. So I'm going to say my initial position, we're going to start our oscillator at rest and at an initial position with no displacement. Let me make sure these are all double equal signs or we'll get an error. And let's just make sure we've got some kind of solution here. It's giving me, okay, so there's going to be some round off error that's going to make its way in. I'm going to ignore that. I don't think that's going to play too much of a role. But I'll comment that out so I don't have to see it because it looks kind of ugly. So we're just going to go ahead and plot x of t. Let me try that again. X of t. Replacing that with the solution we just found. And we'll label our axes. And we're going to be plotting x of t as a function of time, t in seconds. And I need to make a list around this. So that's time t in seconds, and then we'll measure the displacement from equilibrium. Measure that displacement x, and we'll say that's in meters. Now this should give us a plot called with one argument. Yes, I need to tell it what times to look at this for, and I will do this from t equals 0 to 200 seconds. And you can see what's going on pretty nicely here. So we start with 0 displacement at 0 velocity, so we're at 0 here. And then that forcing function starts, and it starts pushing your simple harmonic oscillator. But it takes a while for it to build up some amplitude, and then it overshoots, and then eventually it settles down into that that particular solution, the complementary and the particular solution. So it takes a while for it to get set up here. And you can see this will, we can get different scenarios if I plug in things like different initial conditions. Here we're starting at 1. Let's say I gave it a really big amplitude, started at 100, and I might need to increase my plot range here so I can see it all. You can see here if it was starting really far stretched out, it would take some time for it to settle down into a periodic sinusoidal function. All of this region over here is what we describe as that transient region, where it's looking for the decay of this complementary solution. And once that decays, then you're just left with the particular solution, which will just be a sine or cosine function. With as we've done with every case, DSolve really gets you the opportunity to play and explore and test, which is really what this video series is all about. So once you have this in here, you can try a bunch of different scenarios. You can play with the initial conditions. You can see how that affects the transients. You can say, hey, what happens if I add a whole bunch of damping? And you can see your system decays even with the forcing function. You can say, what happens if I add no damping? There's a whole bunch of things that you can do to explore this. We could say, hey, what happens if I go near resonance? Actually, before I do that, let me actually just plug in what our resonance condition is, because we found that earlier in our particular solution. If I scroll down, if I think I can find it. Where'd you go? No, it was in exploring physics. There we go. Yeah, we can plug in our resonant frequency, copy that. Let's see what our resonant frequency is for this system. We'll put that there, and we'll uncomment it so we can see what that is. And, I need to actually define what omega naught and gamma are. So, as we said, gamma is B over M, and omega naught is the square root K over M. So once I define those, I can figure out what my resonant frequency is. And here my resonant frequency is just a little off of 1. So let's see what happens if I get very close to that resonant frequency. So if I'm on resonance, you can see I get a fairly big amplitude close to 10. If I go just a little bit bigger than that, So we'll make this 1.01. What should happen is our amplitude should drop because on resonance we should have our maximum amplitude. We're around 10 now. If I go to 1.01, not a big enough change, I'll go to 1.1. And you can see that starts to drop down if I go even further away. So this has an amplitude of about 3 or 4. If I go to 1.5, you can see that gets even smaller. Going back to resonance, again, we were at 10. If I go to a smaller value, so say I go to 0.95, you can see the amplitude starts to shrink. You can actually, so we're playing around with the amplitude. We could actually trace out this amplitude curve just by taking points and measuring, kind of doing it experimentally, taking points and measuring how big the amplitude is once the transients have died down and the system is settled into some kind of steady state. Okay, the last thing we're going to show is just how to animate this. So I am going to go ahead and let's change our initial conditions to be starting from rest. So you get, and I'll move us a little bit off resonance to get a little bit more interesting behavior in the transients. I will just show, this is the same animation code we did for a mass on a spring a while back. So you can just copy it down here, pause the video if you need to recreate it. If we hold shift and press enter, you can see we can just animate the same motion as we had before. We've also got some plots there. But if I just animate this, you can see it starts at rest, and then that forcing function picks up. And let me actually, I'm going to run this for a bit longer because I think we did this. Yeah, we did it out to 200 seconds. Slow this way down, and let's get this to run. And you can see you start getting that big amplitude as it goes back and forth. So you can really use this to analyze physical systems. You can both explore the physics from a pure mathematical standpoint. You can look at it as an animation to see what's going on. You can tweak parameters, and hopefully this gives you enough background where you can really start to play and tweak parameters on your own and make hypotheses about what should happen, what shouldn't happen, and then really use the code to test them. Well, that is it for this time. Join us next time where we'll talk about how to play with anharmonic oscillators and look at systems where we're solving nonlinear equations and nonlinear forces. That's all for now. Like the video if you liked it, and if you'd like to see more of these, please click subscribe.